Welcome to lecture 16 for multivariable calculus. Today we just want to accomplish one simple thing. That's to talk about other coordinate systems in 3 dimensions and how to integrate in those coordinate systems. We'll start by reminding you what this 2D situation was quickly. In the 2D situation, we've got a plane, and a point in the plane can be specified in the original way, which is rectangular coordinates, right? So-called because they make right angles with each other. The x-coordinate gives you horizontal displacement, the y-coordinate gives you vertical displacement, and those two numbers specify any point. And then we got more clever and we said, oh, but we can also specify a point in polar coordinates. So that gives me r, the distance from the origin, and theta, the angle off the positive x-axis in the counterclockwise direction there. So those two coordinate systems, you can translate between them. I'm talking about the plane, of course. X is r cos theta, and y is r sine theta. And furthermore, we saw what this had to do with areas. All right, what happened with areas here was that a little piece of area of the plane, right, could be measured in rectangular coordinates very easily as just delta x, delta y. That does give you the area of a rectangle there. But then in polar coordinates, it was slightly more interesting. It was approximately r delta theta times delta r here. And I won't go through that derivation again, but r delta theta is just the arc length of that little segment there. And what that resulted is that when we're going to do a double integral with respect to area, we can just remember that dA is dx dy, which is equal to r dr d theta. So then we translate our double integrals into polar coordinates. We just have to remember to bring this whole term around, including that extra r in the integrand. Okay, so that's a quick review. Now what happens in 3 dimensions? Well, we still have the familiar rectangular coordinates that we've already seen. And so now I've got a little demonstration of that. We've got our x, y, and z coordinates, and you can see them being measured out here. So in the same way, x, y, and z can specify a point in 3-dimensional space. Now we're going to move to 2 more systems, the first of which is going to be very simple and familiar, although it has got a new name. It's called cylindrical coordinates. And the way those work is it's exactly the same as polar coordinates in the x and y coordinates, but z remains z. Right? So that's it. So the translation is trivial. We get r cos theta. Again, y equals r sine theta. And z stays as z. So the translation is quite simple. Now the picture that goes with this is here. Right. So the same point can be specified now, but now with still 3 coordinates, but we've got r, the distance from the origin. Theta is the angle off the x-axis, but be careful here. We're just measuring sort of in the plane, in the xy plane is what theta measures here, right? So be careful when we measure our point. You can drop it down to the xy plane to measure theta. Or another way to specify theta is that it's the angle off the xz plane, if you like, where the positive x-axis. It's a little more of a mouthful, but wherever your point is, if you go to the xy plane and then measure the angle off that to find your point, that's what theta is. But it's the same meaning as with polar coordinates. Right? So that's fairly straightforward. Now, what does that have to do with integrating? Well, when we're doing a triple integral, remember, a typical triple integral looks like a triple integral over a region E of some function dv, right here. And we've already seen that becomes a triple integral over E f of x, y, z. Most of these become iterated integrals, dz, dy, dx, say. and so on. So what about if I want to write this in cylindrical coordinates right here? How are we going to see that? Well, let's just look at what volumes do in cylindrical coordinates, and that will help us figure out this question about volumes here. So let's look here. So here's our picture of rectangular coordinates. You can see that every little, right, if we look at one little piece inside here, right, one little piece of rectangular space, if you like, I see that, what's delta V there? It's just delta X, delta Y, delta Z, and there's no surprise that in the limit we get dV is dx, dy, dz. Right there, so that's the rectangular story. We already knew that we can do triple integrals by just integrating out iteratively through each of our variables. But if we keep that kind of calculation in mind and we move to to cylindrical coordinates, here, we see a very similar story to what we saw in polar coordinates here. Right? So if I chop up my space into cylindrical coordinates here, and then I zoom in on one of these guys here, all right, so a little piece of space, we're going to measure its area. Well, the same consideration that happened with polar coordinates comes into effect. Delta V here, well, I'm just going to write is approximately R delta theta delta R. That gives us that area of the little piece. And since delta Z is the same, we just have another delta Z here. So practical terms, what does that mean for our triple integral here? Well, then dV simply becomes R dr d theta dz. Similarly, just that extra R comes along when we do that. So just like in polar coordinates, in the plane, we need an extra R. You need an extra R here in the in cylindrical coordinates in 3D, right? It performs the same function. Okay, so that's going to be fairly straightforward. When we want to do an integral in cylindrical coordinates, we'll just translate x and y and remember that R in the volume form. Okay, cylindrical coordinates are not bad. They are really a stepping stone, though, onto another, right, coordinate system, and these are the spherical coordinate system. So there's another way to, right, determine where you are in three-dimensional space, and that's where spherical coordinates come in. And these can be a little confusing here. So if we look at this picture there. So our spherical coordinates, there have to be three of them to specify a point in three-dimensional space. We're going to use rho. That's a Greek rho. It's not a p. It's a Greek rho, so it's like a Greek r there. So just like r will be distance, right, in the xy plane, rho is distance in three-dimensional space, and it is distance from the origin still, right? So it does line up in that way. So here's the point I want to specify. Rho will be the distance to the origin here. And then we got two angles, right? So in three-dimensional space, we're going to need two angles to find the direction to point ourselves in. And here's this convention. This is sort of the mathematical spherical coordinates common in mathematics. It is unfortunate that in a lot of different disciplines, there are a lot of different conventions for spherical coordinates. A lot of, say, physicists or astronomers would balk at this convention here. But we're going to stick with the one that's in your textbooks, right? Rather than confuse you with using something that might be in your discipline later, but will contradict what we see in textbooks. So we're going to use two angles. They're the Greek theta and the Greek phi here. And the reason math chooses this convention is that the theta will have the same meaning that it has in cylindrical coordinates. So cylindrical coordinates, theta means angle off in the xy plane, off the x-axis. Same in spherical coordinates. That theta is the same theta, right? And that's the reason here. You'll find theta being this guy in other coordinate systems. So we'll keep theta to mean angle, right, in the xy plane off the x-axis. And then this third angle, the new one, sort of the most confusing one, is this phi here. That's going to measure angle off the z-axis, right? So it's angle here. So when phi is 0, all right, we're going to be along the positive z-axis, right? That's 0 angle. When phi is going to increase, when phi gets to pi over 2, say, it would be in the xy plane here, right? And then it's going to swing down all the way to pi, right, which is the negative z-axis. So phi is a little funny in that regard. So I'll just write out rho, right? That's distance to 0, 0, 0, right here. Theta, as before, angle in xy plane, right here. Also, we can write from positive x-axis. And now phi, some phi, I've heard it's a difference between modern and ancient Greek. I'm not even sure what is best. I'm going to say phi here. Phi is the angle off the z, or positive z-axis. So it's important to note that we're going to keep phi in the range from 0 up to pi only. We don't let it go wrap around past pi, because then we would have, right, different ways of specifying the same point. Right? So that's our definition of spherical coordinates. We can quickly work out a nice translation between all of our systems of coordinates. If we go through cylindrical coordinates, this becomes actually easier, I think. So we know how to translate into cylindrical coordinates: r cos theta, r sine theta, and z is z, right here. But now when we want to translate into spherical coordinates, we can do that most easily by just translating what r and theta are. So in this picture, you see on the left here, this distance down here, that's r. And this distance here, that they make a right angle, that's z. And so we can do a quick translation from z into spherical coordinates by seeing that z is simply, right here, rho times the cosine of the angle phi. Right? You can think of it as, right, phi is there, it's also here, right? By internal angles, that's also phi. So we get that z is rho cos phi there. And if we remember that, then it's clear that r here is rho sine phi. So we're just going to get rho sine phi, and then cos theta to get x, and rho sine phi, and then sine theta to get y. So there's our translation between our three coordinate systems, and I think it's easier to kind of see it if you do it in stages this way. Okay, so lastly, let's talk about volumes in spherical coordinates. And again, this gets a little confusing, but there's only just one at the end. There's only one formula to remember, and it's not so bad. So let's look how space is divided up when we look at little changes in our spherical coordinates here. I'll rotate this picture a little bit so you can see it. And here's kind of how we divide up space into, when I look into chunks of rho, phi, and theta. The change in rho you can see, right, by the sort of thick wall here. You can think of this as a wall of a sphere, which is, right, kind of where the name comes from. Right? If rho is fixed, we end up on it literally on a sphere. So a little change in rho is the thickness over here. Let's zoom in and trace out a piece of this. So we're looking at the same guy here. So a little piece of space here would be like this piece over here. And if I'm going to find its volume, right there, it's a little tricky to think about, but the distance, right, along here, right, vertical distance there, that's not so bad. That's rho delta phi. All right, so that's going to be delta v here is approximately rho delta phi. Right, that's the length on the inside here. The thickness there is just delta rho. That's the thickness here. And then the tricky one is kind of on the inside here, or rather the distance this way, right here. That is a little bit trickier to measure, because you have to realize that that distance there, kind of laterally, like sort of along a latitude line, if you like, right? That distance there depends on phi, right? Notice that when phi is close to 0, so up here, that's not a very small difference, right? So it depends on phi and theta there. When phi is large, right, down here, right there, a little change in theta is really big. So in order to figure that out, we really need this distance, right? The r distance comes into play. So to make a long story short, we're going to get this guy times rho sine phi delta theta here. And so when you put that together, we get rho squared sine phi d phi delta phi delta rho delta theta. I usually make some lame frat joke with all these Greek letters at some point in here. So the uptake is that when I go to compute the volume form, right, I need to remember this guy comes along. So rho squared sine phi is going to be in the integrand, right? D rho d phi d theta. Right. Every time I do a triple integral in spherical coordinates, that's the translation, right, I'm going to need in order to do it here. Now in class, we'll do lots of examples to try to get used to this. I think the challenge is, again, a geometric challenge, right? Choosing your limits of integration for certain regions and how to do it, right? Theoretically, all you really need to remember is, right, are these formulas for translating to different coordinate systems. R, dr, d theta, dz for cylindrical coordinates, rho squared sine phi, d rho, d phi, d theta for spherical coordinates. But it's a good idea if you have some idea where these things come from. It helps you, will help you understand what's going on and set up your problems the correct way.